Thank you very much, Philip, for the invitation, and thank you very much for the introduction. So it's a pleasure to speak in this seminar. And today I want to talk about joint work with Ben Howard on Kudla-Rapoport divisors on unitary Shimura varieties and their arithmetic volumes. So basically, on arithmetic varieties, we want to compute volumes of natural subvarieties. And somehow for the arithmetic varieties, we look at unitary Shimura varieties, and the subvarieties are basically given by unitary sub-Shimura varieties. So this is a variant of, or in some sense, extension of by now classical results on, well, on the one hand, results on the geometric analogs, the complex volumes of Shimura varieties and their subvarieties. So this is one direction, and in some sense, these are arithmetic analogs. On the other hand, in this arithmetic setting, the first work that was done was in the very classical case of modular curves, and maybe I want to start with that. So I want to look at modular curves. So basically, I want to look at the modular space of elliptic curves over spec C. So the complex points are just the usual modular curve. So you have the other half plane modulo the action of SL to Z by fractional linear transformations. And this modular curve comes, I mean, it's a modular space of elliptic curves. It comes with a universal elliptic curves. And this gives rise to a natural line bundle. Namely, if we look here at the universal elliptic curve, then we can, there was a little confusion. Then we can look at the relative cotangent bundle, and this gives rise to the Hodge bundle on the modular curve, or you can say it gives rise to the line bundle of modular forms of weight 1 on the modular curve, a very natural line bundle. And this line bundle comes with a natural metric also. So how is this defined? So I define this metric fiber-wise. If we have a point here, tau, in the modular curve, then there's a corresponding elliptic curve for this point. And if we have something in the fiber as tau above tau, so this corresponds to a differential in the elliptic curve above tau, then we can just take the L2 metric of this differential. So we integrate over the fiber, the S tau, wedge it with its complex conjugate. This gives us the L2 metric of this guy, and then it has to be normalized by some power of 2 pi I. And in this way, on every fiber, we get a Hermitian metric, and this varies smoothly if we vary the base point tau, and in this way, we get a Hermitian metric on this line bundle. And then we get a pair, namely, we have the line bundle on this modular space Y together with a Hermitian metric, and this is called a Hermitian line bundle. So it's a line bundle on the arithmetic variety together with a Hermitian metric, and the isomorphism classes of such Hermitian line bundles, they form the arithmetic Picard group denoted by pic hat of Y. Okay, so we have this Hermitian line bundle. This is now on the so to say, the open modular curve. We can extend it to the compactification. So this modular space of elliptic curves has a natural compactification constructed by Dirichlet-Rapoport, denoted by Y bar. So it's a compactification of Y uh, and the line bundle extends to it. The metric doesn't really extend. It has some singularities along the boundary, along the cusps, but these singularities are rather mild. So they turn out to be of logarithmic type. And what we get then is on the compactification, a Hermitian line bundle where the metric is allowed to have mild singularities at the boundary, at the cusps. So here, mild singularities are logarithmic singularities. And in some sense, there's a generalization of this arithmetic Picard group where you allow the metrics to have these mild singularities, these logarithmic singularities. This was constructed by Burgos, Kramer, and Kühn, this extension of Arakelov theory in the sense of Gillet-Soulet. And somehow our Hermitian Hodge bundle gives us a class in this arithmetic Picard group in this slightly generalized sense. Okay, so this is a nice object, and we want to compute some invariants of it. So the first thing we can do is we can look at the complex volume of the modular curve. This is, of course, very well known. We can look at the Chern form of this Hermitian line bundle. How do we get that? We take a rational section S of the line bundle, then we can take its metric, then we get a function on the modular curve. And then we take the logarithm of it and then DDC, so basically del bar, the differential with the right normalization. And if we compute that, this is a very easy exercise. We get basically the invariant volume form on the complex upper half plane up to a factor of 1 over 4 pi. So this Chern form is integrable, and already by work of Mumford, it can be used to actually compute the class of this line bundle. In particular, this Chern form is also the Kähler form associated with the natural invariant Kähler metric on the modular curve. So also, if we want to compute the volume of the modular form of the modular curve in sense of Kähler geometry, then we just have to integrate this Chern form. And we know what happens. We can compute the complex volume of the modular curve. And this is just, in some sense, the Chern form itself is already, it's a 1-1 form. It's in top degree. We just integrate over the modular curve. And then we know, okay, what is this? This is basically the volume of the fundamental domain. And with this normalization here of the volume form, we get 1 over 12 here as the volume. And 1 over 12 is somehow the negative of Riemann zeta at -1. So the upshot is that it's given by a special value of some natural zeta function. Okay, so this is the complex volume. We can also look at the arithmetic volume, because after all, we really have a line bundle on the integral model of the modular curve together with a Hermitian metric. So we can use Arakelov theory. So let's look at that. So let's look at the arithmetic volume of the modular curve. So we have this Hermitian line bundle in the arithmetic Pk group of the modular curve over the integers. So this is now really an arithmetic surface. So it has dimension 2. Somehow, if we have a Hermitian line bundle, we can look at its Chern class, which is a class in the arithmetic Chow group, the first arithmetic Chow group. So these are arithmetic divisors, and arithmetic divisor is a pair given by a divisor on the arithmetic variety together with a green function. Green function that computes the cohomology of the divisor. Somehow this first Chern class is given in an easy way. So one just takes a rational section of the line bundle of our L hat. If we take a Hermitian line bundle, we take a rational section, and then we can take its divisor on the integral model. And for the green function, we just take negative log of the Hermitian metric of the section. And this gives then such a green function for this guy. So we get a arithmetic divisor. Okay, and now as for usual Chow groups where we have an intersection product, also in this Arakhelov setting, there is an intersection pairing. So we can pair arithmetic divisors with other arithmetic divisors, and then we get an element in Chow 2. So this would be codimension 2 cycles together with green currents. And since Y has total dimension 2, this is the top degree arithmetic Chow group. And from the top degree arithmetic Chow group, there's an arithmetic degree map. So this goes to R, and in fact, we can take the arithmetic degree map and we get a real number. And we can now define the arithmetic volume of our Hodge bundle, or more general, we could take any Hermitian line bundle. We just take the intersection product in this arithmetic Chow ring with itself in order to get to the top degree arithmetic Chow group, and then we take the arithmetic degree, and this gives a real number. And this is in some sense a natural invariant of the Hermitian line bundle. Okay, so the question is, what is this for the modular curve? And this is a very nice, beautiful result of Jean-Benoît Prost and Ulf Kühn from 1999, I guess, around that time, which says that the arithmetic volume of this metrized Hodge bundle on the modular curve is given by the logarithmic derivative of Riemann zeta at -1. So in some sense, for the complex volume here, we got zeta of -1 or the negative of it. And for the arithmetic volume, we get the logarithmic derivative of this zeta function at the same place. And this is a picture that holds in greater generality. So in general, one expects these arithmetic volumes to be given by logarithmic derivatives of zeta functions. So in some sense, in the Kutler program, such quantities would be related to constant terms of derivatives of Siegel-Eisenstein series, which are typically given by certain zeta functions. And then if you take derivatives, you get derivatives coming in. Also, there are general conjectures due to Mayo and Rössler that predict that somehow these self-intersection numbers of Hermitian line bundles, say on Shimura varieties, are given by logarithmic derivatives of Artin L-functions. Okay, so this is a very special case. This is the modular curve. Of course, one can look at this in greater generality. We don't have to focus on the modular curve. We could take any PEL Shimura variety M. It comes with a universal abelian scheme over it. And therefore, we have a Hodge bundle. So we take the top power of the relative cotangent bundle and push it down to the base. This gives us a line bundle, lateral line bundle, the Hodge bundle on this Shimura variety. And these top degree differentials, we have a natural metric which is given again by the L2 metric. So one just computes the L2 norm of such a top degree differential, and this endows then this Hodge bundle with a natural Hermitian metric, which is somehow the analog of this Petersson metric that we were looking at before. And now one can look at that in different cases. So here I listed a few cases where work was done. So for instance, instead of looking at modular curves, one can look at quaternionic Shimura curves. That was done by Kudla-Rappaport and Yang for Shimura curves over Q, and more recently by Yuan for Shimura curves over arbitrary totally real base fields. There's work of José Burgos and Ulf Kühn and myself, where we looked at the case of Hilbert-Moyer surfaces. Barbara Jung and Anna von Pippich looked at the Siegel threefold. And there's work of Fritz Hörmann, who looked at ON2, so Shimura varieties associated to orthogonal groups. And he computed such arithmetic volumes, I guess up to a few bad primes dividing the discriminant. Yeah, and in our work with Ben Howard, we looked at the case of unitary Shimura varieties. So now I want to look at this in more detail. So let me introduce the basic setup here. So K should be an imaginary quadratic field, which we view as a subfield of the complex numbers. The discriminant is minus D, and I want to assume that this discriminant is odd for technical reasons later. And then we can look at the unitary Shimura varieties, and one way of looking at them is as moduli spaces. So we look at the moduli space, which I don't denote here as Mn minus 1, 1. So this should be the moduli space of triples A, iota, psi, where A is an abelian variety of dimension n. Iota is a complex multiplication, OK action, where the OK action should have signature n minus 1, 1. So this is a condition on the induced action on the Lie algebra of the abelian variety. And this and there should be a principal polarization psi, which should be compatible with the OK action. So we can look at that over the complex numbers, and then there's a moduli space. It has a complex dimension n minus 1. But one can also use this modular description to construct integral models. So for instance, there's work by Pappas and Kremer who show that there exists a regular integral model over the ring of integers of our imaginary quadratic field over OK. This is flat and regular. It has dimension n, total dimension n. And also it has a canonical toroidal compactification, which I denote by M bar. Okay, so this is nice. This is a nice Moyer space. We can look at it in a bit more detail. It turns out that this has a decomposition into closed and open substacks, MV, which are indexed by similarity classes of Hermitian spaces of signature n minus 1, 1, that admit a self-dual OK lattice. And here, this similarity is a technical notion. It means isometric after possibly rescaling the Hermitian form by a positive rational factor. And there's a dichotomy. So if n is even, it turns out that a similar is just the same as isometric. So you can say here the disjoint union runs over isometry classes of such Hermitian spaces. And if n is odd, then it turns out that all these K immersion spaces are similar. So all these spaces that admit a self-dual OK lattice. Okay, so this is just technical thing in some sense. It's important here that these MV are indexed by these K Hermitian spaces V, and this MV can be viewed as an integral model of a Shimura variety associated to the general unitary group of V with a suitable level structure. And here we're again in the situation that we can look at the universal abelian scheme, say over such an MV, and one can look at the relative cotangent bundle at its top power, and this gives rise to a Hodge bundle. So this is first a line bundle on MV on this integral model of this unitary Shimura variety. Again, it has this L2 matrix, so there's a natural metric on this line bundle. So it really gives a Hermitian line bundle, so a pair of a line bundle on this integral model together with a Hermitian metric on the complex fiber. So it defines something in the arithmetic Picard group. And this arithmetic Hodge bundle is the object we want to look at, and we want to compute associated volumes. Okay, and I want to give you the main result, and in order to give you the main result, I need to introduce a little more notation. This looks a bit clumsy or maybe a bit heavy at first sight, but it's not so bad. So first of all, we have this quadratic extension given by the imaginary quadratic field. There's a quadratic Dirichlet character associated with it. So it's just epsilon of x is x over d. So it's given by the Legendre symbol. And we can look at the associated Dirichlet L function. So this is here the Dirichlet L function. And here the argument is shifted by k. And so this beta k is basically just this Dirichlet L function shifted by k. And then there is some gamma factor for the normalization. And there are some bad Euler factors. And these bad Euler factors are somehow related to the invariant of the Hermitian space V. So this inf L of V is the local invariant of V. So this local invariant is given by the local Hilbert symbol. So one takes the Gram determinant, takes the local Hilbert symbol with the discriminant of the imaginary quadratic field. So this is the local invariant of V. So this enters in these bad Euler factors. And also I should say that here we have the Dirichlet L function, and I wrote epsilon to the k. Epsilon is a quadratic Dirichlet character, so if k is even, then this will be trivial. And I should say that in this case, when k is even, I understand by this Ls epsilon k just a Riemann zeta function. So this is for short here. Okay, so in other words, this beta k is a shifted Dirichlet L function or Riemann zeta, and it's shifted by k. Okay, and in terms of this, one can give the formula for the volumes. So this is one of the main results in this work with Ben Howard. So first of all, there's a formula for the complex volume of this unitary Shimura variety. And this complex volume can be given in terms of these shifted Dirichlet L functions or Riemann zetas. So it's basically the product of all of these. So beta 1, we have a shift by 1, and then beta 2, we have a shift by 2, and so on up to beta n. So this gives the complex volume. And now the arithmetic volume somehow in accordance with these conjectures of Mayer-Rössler is also computed. And it turns out, in accordance with these conjectures, that we have the logarithmic derivatives of these L-functions coming in. So the same L-functions at the same places evaluated, and these give the arithmetic volume. And the arithmetic volume, again, is given by, I take the Hermitian line bundle and use its arithmetic self-intersection to top degree in this Arakelov sense, and then I take the arithmetic degree. Okay, and then also there's some little normalization constant, which is maybe not so important here. So the important part is it's the logarithmic derivatives of these same L functions that appear here. Okay, and so this is really a formula that is true on the nose. So there's no ambiguity at any bad primes. So this is really at all primes. And so this is also one reason for this assumption that the discriminant of the imaginary quadratic field should be odd. So in order to be able to state it in this precise form, we have to assume that. Okay, so this is the result. And now let's look at how one can prove something like that. Well, what's the idea of proof? The basic idea is one uses induction on the dimension. Okay, so we have to have a start for the induction, and here as a base case, we look at the case when n is 2. So then the signature of the Hermitian space would be, I mean, it's always n minus 1, 1. So then the signature would be 1, 1. And these unitary Shimura varieties in this case basically boil down to modular curves or Shimura curves. So this is because the special unitary group of signature 1, 1 is just SL2R. The corresponding Hermitian space is just the upper half plane. And so in this case, one can relate this Shimura variety MV to a modular curve. And this also works over the integral models. And one can reduce this result on the volumes on the corresponding results for modular curves and Shimura curves. So in some sense, these results due to both Kuhn and Kudla-Rapoport and Young. Okay, so this is the base case. And how do we do the induction? Well, there we use an arithmetic version of the Hirzebruch-Sage theorem. So the Hirzebruch-Sage theorem says that if you look at a Hilbert-Moyer surface and you look at the Hirzebruch-Sage divisors on it, you can form a generating series, and it turns out that this is a modular form with values in cohomology. And there are a lot of generalizations of this result, for instance, due to Kudla and Milson. So in general, cohomology classes of special divisors are given by Fourier coefficients of certain Siegel-Moyer forms. And in the Kudla program, one actually looks for arithmetic variants of such results on integral models of Shimura varieties. And it is known that somehow Kudla-Rapoport divisors on unitary Shimura varieties, which are the analogs of these Hirzebruch-Sage divisors, they are the coefficients of a Moyer form, of an elliptic Moyer form of weight n. And one can use the modularity of these Kudla-Rapoport divisors to relate the volume of our Shimura variety MV to volumes of similar Shimura varieties in dimension 1 less. And this is somehow how the induction step goes. The volumes of MV will come up by looking at the constant terms of these generating series of Kudla-Rapoport divisors. So this is somehow how this induction step goes roughly. Okay, so in order to describe this in a bit more detail, we need to introduce these Cutler-Rappaport devices. How are they defined? So this is what I want to explain next. So for every positive integer, or actually non-negative integer, there's a Cutler-Rappaport divisor Zn, and I want to define it. And in order to define it, it turns out that it's useful to replace this modular space MV by a finite étale cover. Namely, we take the product of MV with M1, 0. So this is the modular space of a billion varieties in dimension 1, so elliptic curves, with OK multiplication of signature 1, 0. So this is really modular space of CM elliptic curves where you have complex multiplication by OK. So this is so if you look at the complex fiber, this is just finitely many points, and we replace somehow our MV by this finite étale cover. And why do we do that? One reason is that on this finite étale cover, so if we take this product, then if we take a point in this space, so this is now given by a pair E, A, where E is a CM elliptic curve and A is a CM abelian variety, there is a natural OK module associated with it called the Hom space, and these are the OK linear homomorphisms from E to A. And on this space, there's a natural Hermitian form, and this can be used to define these Cutler-Rappaport devices. And how does this Hermitian form work? So if we have two elements in this Hom space, say X and Y, then we can look at this little diagram. So X is a homomorphism from E to A. Okay, so we can use it to go from E to A. And A has a principal polarization, which is compatible with a complex multiplication. So we can go from A to its dual. And then on the other hand, from A dual to E dual, we have the dual of the homomorphism Y, so the other guy. So we can go somehow from E to A dual, to E dual, and then we can take the inverse of the principal polarization on the elliptic curve to come back to E. And somehow this composition defines then an OK linear endomorphism of the elliptic curve E. And these OK linear endomorphisms are just given by OK. So in other words, for a pair of homomorphisms, we get a number in OK. And this defines a positive definite Hermitian form on this Hom space. And this can now be used to define Cutler-Rappaport divisors. So the Cutler-Rappaport divisor Zm should just be the modular space of triples. So we have an E, we have an A, so something in this in this product here, together with a with an element X of this Hom space, which should have norm M. And the locus of these triples gives a divisor on the modular space. And this is the Cutler-Rappaport divisor of discriminant n. Okay. If you look at that in the complex fiber, then this is just gives you back the special divisors that Kudla and Nilsson looked at, and in some sense the natural generalization of these sorts of Rosage divisors. Okay. Now, in order to work with that, we have to relate at least some of these Kudla-Rappaport divisors to unitary Shimura varieties in dimension 1 less. And this can be done in the case where the index is a prime which is split in k. So if we take a split prime and we take a vector x in the Hermitian space of norm p, then we can look at the orthogonal complement v prime. And then this is a Hermitian space of signature n minus 2, 1, dimension 1 less. And it turns out that this space admits also a self-dual OK lattice. And this is due to the fact that P is split in the imaginary space. So you can compare the local invariants, and then the local invariants dictate whether you can find such a self-dual OK lattice. And in this way you can. And then you can look at the unitary Shimura variety associated to this space V prime. And it turns out that the Kudla-Rappaport divisor of discriminant P is basically, so this is why I wrote here somehow quotes, is basically a bunch of copies of this MV prime. And it's somehow P to the n minus 1 plus 1 copies of this MV prime. And also it turns out that if we pull back our Hodge bundle via the map from MV prime to this Kudla-Rappaport divisor sitting inside this MV, then we get the Hodge bundle on this V prime Shimura variety. So everything is compatible. This is quite nice. So this is in some sense a nice special case of these Kudla-Rappaport divisors. You just find similar unitary Shimura varieties in dimension 1 less. Okay, and now what's this arithmetic analog of the Hirzebruch-Sacquet theorem? In order to formulate it, one has to do a little technical things. So first of all, we want to do everything on the canonical toroidal compactification. So we have to complete our Kudla-Rappaport divisor by some boundary divisors, Bm. Okay, but this is just a technical thing. You can basically forget about it. And then also you want to define an Arakelov divisor, so a divisor together with a green function. And this gives you then a divisor Z hat of M, Arakelov divisor, which has a class in the first arithmetic Chow group. And this is given by the divisor Zm star together with a suitable green function that is a green function in the sense of Arakelov theory. And one way of defining such green functions is using generalizations of the Borchards' regularized theta correspondence. One takes the unique harmonic mass form of weight 2 minus n for the modular group gamma 0 d, so level d, whose principal part, so the singularity at infinity, is q to the minus m. And then one can plug it in this Borchards machinery and one gets a green function. And in this way, one gets an Arakelov divisor. Okay, so this is for positive m. Then we also have to say what we do for m equal to 0. For m equal to 0, we just take the negative of the metrized Hodge bundle as the Kudla-Rappaport divisor of index 0. Okay, so now we have for all non-negative integers such Arakelov divisors or classes in the arithmetic Chow group. And in the spirit of Hirzebruch-Sacquet, we can look at the generating series. So we can take these Arakelov divisors and form a formal power series with it, like this. So a priori, this is a power series And it has coefficients in the first arithmetic Chow group of this unitary Shimura variety. And the result that Ben Howard, Steve Kudla, Michael Rappaport, Tonga Young, and I proved about this generating series is that it's actually the Q expansion of a Moyer form. So it's an elliptic Moyer form of level D, so level gamma 0 D, with quadratic character epsilon to the n. So if n is odd, then non-trivial character. If n is even, then trivial character. And it takes values in the first arithmetic Chow group. And what do we mean by that? We mean if we take a linear functional on this arithmetic Chow group, for instance, given by taking the intersection pairing with arithmetic cycles in complementary degree, if we take a linear functional and apply it here coefficient-wise, then the coefficients will be mapped to complex numbers. And the assertion is for every such functional, if we apply it coefficient-wise, we get the Q expansion of an elliptic Moyer form. So that's the analog of the Hirzebruch-Sage theorem in this setting. Okay, so what does this help us? So a priori, there are no volumes around here, but what we can do now is we can take particular functionals that we apply here to this generating series. So what we can do is we can pair with the n-1th power of the metrized Hodge bundle. So we take the self-intersection n-1 times of this Hermitian line bundle. So this gives a class in the Chow group in degree n-1. We can pair it with this generating series. The coefficients will be then in the top degree Chow group, and then we can take the arithmetic degree to get numbers. So in other words, here the coefficients are the arithmetic intersections of this power of the Hodge bundle with these arithmetic Kudla-Rappaport divisors. And the modularity in particular implies then that this generating series is a Moyer form, which is quite nice because this somehow gives many relations between somehow the coefficients of this generating series. And one nice thing is, if you remember here, the constant term of this generating series was given by basically by the metrized Hodge bundle. So if we look at the constant term here, so the m equal to 0 term, then we have here the metrized Hodge bundle intersected with the n-1 power of the metrized Hodge bundle. So what we really get here in the constant term is the arithmetic volume. So we can hope to get some information about the arithmetic volume from this modularity. I mean, so that's now the basic idea. And how does this work? Well, we can compare our generating series with a natural Eisenstein series in this space of Moyer forms for gamma 0 D, weight n. So somehow D was an odd discriminant of an imaginary quadratic field. So in particular, it's square free. The cusps of the Moyer curve for gamma 0 D are somehow in bijection with the divisors of D. And for every cusp, you have an Eisenstein series, and then there is a natural linear combination of these Eisenstein series for the different cusps that I denote by E of tau in this space. And here these gamma R are just some fourth roots of unity that are given by certain Weil indices. Not so important maybe. So important thing is just that this is a particular Eisenstein series. And then there's a conjecture that says that this degree generating series that we wrote down on the previous slide should be simply a multiple of this Eisenstein series. And the proportionality factor should be the arithmetic volume. And also part of this conjecture is that the arithmetic volume should be given by the formula that was claimed earlier. And so what can we say about this conjecture? So we can prove part of it. So what can we prove? So we can prove that, I mean, we know that on both sides of this equality, we have some modular forms, and we can show that they are equal. Well, we can show that half of the Fourier coefficients agree, namely for all integers m with a property that the quadratic character evaluated at m is 1, the Fourier coefficients agree. And also the constant term, so the arithmetic volume, is given by this claimed formula. And remember, the claimed formula, what was this formula here? So this somewhat lengthy formula, but somehow this explicit linear combination of logarithmic derivatives of, oops, little confusion, of these Dirichlet L-functions. Okay. So how can we prove that? The idea is to use this modularity in an extensive way. Okay, again, we want to prove this by induction. If n is 2, then one can reduce to the result of Boost-Kuhn and Kudler-Rappaport-Young. This is maybe not so interesting because this is already known in some sense. How do we do the induction step? So we assume now that n is bigger than 2. And now we look at a prime P, which is split in the imaginary quadratic field K. And in this case, we know that the Kudler-Rappaport divisor ZP was essentially the unitary Shimura variety in dimension 1 less. And this is what we try to use. So this was the content of this proposition that I had earlier. And we can use it to compute the pth coefficient of this degree generating series. So where we took this intersection. Namely, how do we compute it? Well, what was the pth coefficient of this degree generating series? Well, the pth coefficient of A hat was given by this ZP hat. So somehow the pth coefficient is exactly this quantity here. And how is this given? Well, so we have to compute this intersection here, and this intersection can be computed by taking the height of the Kudler-Rappaport divisor ZP with respect to the Hermitian line bundle omega hat for V, plus the integral of the green function for the Kudler-Rappaport divisor. So this is the second part. So this is just, in some sense, the definition. And now the height here, how is this computed? Well, you have to take, you have to pull back the omega V to ZP and take its top power and take the degree. Now the point is the ZP is essentially the Shimura variety in dimension 1 less. So somehow Shimura variety associated to this V prime. And the pullback of the Hodge bundle is again the Hodge bundle for this Shimura variety in dimension 1 less. So this height gives as a contribution exactly the arithmetic volume of this unitary Shimura variety in dimension 1 less. And then you have a factor in front, BP, which is the pth coefficient of this Eisenstein series. So here the Eisenstein series has coefficients B, M, S0. Okay. And then for the integral here of this green function, of this Vp, one gets the logarithmic derivative of the coefficient of this Eisenstein series. What do I mean by that? Well, the Eisenstein series really is not only a holomorphic Moyer form, it also has a dependency on a spectral parameter S, and I can take the derivative with respect to the spectral parameter, and then one sees that the integral of the green function is given by the logarithmic derivative of the coefficient. And this is true up to some rational multiple of log p. And the point that we don't get this on the nose a priori is that it's a bit difficult to control all these maps at primes dividing all the level, the level of the CP, so one has a priori some ambiguity here. But now the good thing is, if one looks at this, the sum here, it turns out that this is the claimed formula for the arithmetic volume, so the CV. So what one gets here is the pth coefficient of the degree generating series is the pth coefficient of the Eisenstein series times the claimed formula for the degree plus some rational multiple of log p. Okay, but what does this mean? This means that if we take the degree generating series and add the claimed formula for the volume times the Eisenstein series, then some of the coefficients are just of the form alpha p times log p, namely all coefficients with index p where p is a split prime. And now one can use results of Belaish on Galois representations associated to Moyer forms to deduce that these alpha p have to vanish for all such p. This is a consequence of these results. And in other words, this tells us that if we compare the degree generating series with now the multiple of the Eisenstein series given by the arithmetic volume of this Hodge bundle, then this is equal to this claimed formula for the arithmetic degree plus, the volume of the arithmetic degree. And also, basically by construction, this guy is a cusp form. And now one can look at the growth of these coefficients. They are the coefficients of an Eisenstein series, and they grow too fast so that this quantity can be a cusp form. And from the growth, one deduces that this can only be the case if this quantity is actually zero. So in other words, this volume of the metrized Hodge bundle has to agree with the claimed formula, and this basically concludes the proof. Of course, there are quite a few technical subtleties that I swept under the rug, but this is really the rough idea. So, and this then somehow proves the arithmetic volume formula, for the constant term. So somehow the arithmetic volume of the unitary Shimura variety is the claimed formula. And also it proves the arithmetic volume formula for this, gives a formula for these arithmetic Hirzebruch, arithmetic Kudla-Rappaport divisors. And this basically gives then the theorem with Ben Howard. And that's basically all I wanted to say. So thank you very much for your attention.